Okay, good. So good morning or evening, everyone, and welcome to our 18th ECS and Cloud Feedback Symposium. And before we start, and I have a couple of notes to remind you, especially for those who are new to our symposium. So as always, this time we have a 3 AGU style talks, and after each talk, we have time for questions. And in the end, we usually have a short general Q&A section where we can discuss more. So if you have any question or comments during the talk, please type them in the chat. And if you prefer to speak, please use the raise your hand function and we will unmute you. I think you're also able to unmute yourself. As always, if you like to give a talk in the future events, please contact our committee members, which are listed here. Also, if you have any suggestions or comments for the symposium, please let us know, and we would love to hear them. So, so more information can be found on our website. I think you can also find this link in the emails that we send out. And particularly, we upload the recordings of all the presentations after each event in a timely manner. So if you need, you can go back and revisit them. So without further ado, let's welcome our first speaker today, David Bonan from Caltech. I think he's gonna talk about how radiative feedbacks shape the response of the hydrological cycle to global warming. So it's all yours, Dave.
Cool. Let's see. All right, yeah, so thanks. Thanks for the organizers for allowing me to speak in this. This is work that I've largely been doing with Nick Seiler at OSU, Gerard Rowe and Kyle Armour at UW, Nicole Feld at UCSC, and then Ian Eisman and Emma Beer down at Scripps. And it's about how radiative feedback shaped the response of the hydrologic cycle to global warming. So I thought it would be good to just start off by showing the patterns of warming and P-E changes for 20 different GCMs under 4 times CO2. So this is the long-term kind of climate response. And what you can see is that, GCMs agree on kind of some notable features of the climate system of Arctic amplification and delayed Southern Ocean warming. And then with P-E changes, they largely show that the regions that were wet get wetter and the regions that get dry get drier. And if you can see this just by the kind of increase in precipitation on the equator where the ITCZ is, and then this drying of the subtropics. But GCMs also kind of show a couple other features. They show expansion of the subtropical regions here in the southern and northern hemispheres. They show a narrowing of the ITCZ region, and they also show kind of a poleward migration of the storm tracks as well. And so in some seminal work by Held and Soden in 2006, they kind of came up with a nice scaling to kind of explain this wet gets wetter, dry gets drier paradigm. And what they basically came up with is said that if you take P-E, which is equal to the convergence of mass-weighted, vertically integrated moisture flux here, you can assume that this change in latent energy transport is just simply a change in lower tropospheric specific humidity with no changes in atmospheric circulation and no changes in relative humidity. And if that's the case, then a perturbation or a change in that latent energy transport is simply going to be the Clausius-Clapeyron relation times the change in temperature times the climatological latent energy transport. And so the divergence of this actually equals P-E, and you get the P-E changes is simply just a function, an amplification of the climatological pattern of times the temperature change, basically. And so plotted over here on the right is the zonal mean change in P-E in black for the GCM, and then in red is this Held and Soden scaling. And you largely see that it does capture the wet gets wetter, dry gets drier paradigm. But there's kind of notable regions where you see there's this mismatch. So there's this kind of change in the ITCZ position and increasing tropical precipitation that the scaling doesn't capture. There's kind of a shift in the storm tracks and the expansion of the subtropics that it doesn't capture. And there's kind of this overshoot or amplification of P-E changes in the higher latitude regions. And so what I want to focus on today is actually a new perspective, one that was introduced by Nick Seiler in 2018, which is relating P-E changes to latent energy transport and downgrading energy transport in a moist energy balance model. And so in blue here is this moist energy balance model, which I'll describe in further detail in a second. But you can see that it largely captures this increase in P-E on the equator, the drying of the subtropics as well, and then this kind of more muted high latitude P-E changes in both hemispheres. And I think notably, it also captures this kind of this narrowing of the ITCZ region, which you can kind of denote here by these climatological P-E0 patterns or values. And it kind of captures the migration of the mid-latitude storm tracks. And so how this energy balance model works is you basically take the net heating of the atmosphere here, which is a function of radiative forcing, ocean heat uptake, and your radiative feedbacks. And you set that equal to atmospheric heat convergence, which you represent as just a down gradient diffusion of near surface moist static energy. And so what I plotted here on the right is just the patterns of zonal mean patterns of radiative forcing, ocean heat uptake, and the net radiative feedback diagnosed from CMET5 models into that same 4 times CO2. And from here, you can actually approximate just a temperature pattern and changes in atmospheric heat transport. But to get the P-E changes, you need to kind of apply this Hadley cell parameterization. And so what we do here is we apply a weighting function that's Gaussian on the equator that basically partitions this atmospheric heat transport into a function of the Hadley cell and mid-latitude eddies. And so essentially this is 1 on the equator and it goes to about 0 by about 45 degrees north or south. And once you have that, you can take this atmospheric heat transport by the Hadley cell and set that equal to the mass flux of the Hadley cell times the gross moist stability. And so we know this part of the equation. And if we approximate the gross moist stability as just some scaling of the gross moist static energy or the moist static energy on the equator and the difference between that meridional variations, you can get the gross moist stability. And so from there, you can actually approximate the stream function. And so once you approximate the stream function, you just flux moisture back up gradient rather than down gradient, while still diffusing everything else down gradient. And so then effectively your moisture transport is going to be a function of Hadley cell transport and eddies. And then again, the divergence of this is now going to be equal to P-E. And so this is the P-E in the moist energy balance model. And I showed it earlier, but if you start to look at this across models, you can see that it really captures the P-E changes quite well. So again, this is the P-E change under 4 times CO2. Black is the GCM, red is the Heldon-Soden scaling, which is just an amplification of the climatological pattern, and blue is now this energy balance model. And you can see that it does kind of capture this increase in P-E on the equator and this kind of shift of the ITCZ region. It also captures the more muted responses in the higher latitudes as well. And kind of important for this study is it kind of captures this climatological narrowing to, or not climatological, the narrowing of the ITCZ as well, which you can see from these climatological patterns right here. And so you can do this for all the 20 models that we have. So that was a more amplified hydrologic response. Here's a more muted response in CCS74. You can see that the energy balance model does kind of capture the same structure and the better higher latitude subtropical drying responses that we see in the GCMs. So you can start to flip between models here and you can see that it really does kind of capture the intermodal spread among these models. And what I want to kind of highlight is that if you just take an average of the P-E response in various regions like the extratropical high latitudes, subtropics, deep tropics, or the subtropics and extratropical high latitudes in the northern hemisphere, and just plot that against the GCM, you can see that the energy balance model, which is in blue, captures a lot of intermodal variance. So especially in the high latitudes, it's capturing approximately 80% of the intermodal variance. And even in the tropics, it's capturing 50%, whereas the Heldon-Soden scaling isn't capturing much of the intermodal variance. And so we can begin to ask, well, what's going on here and why is this? And so I'm going to gloss over some things, but we've traced this down to the spread and the feedbacks across CMET5. And what I want to kind of highlight here is just 2 different models with 2 different responses. So in the top panel here is CCSM4, which is a more muted response. And in the bottom panel is the Muroc ESM, which has kind of a more amplified hydrologic response. And you can see the more muted response, the Heldon-Soden and moist energy balance model, agree in the tropics, less so in the high latitudes. Whereas in the Muroc ESM response, which is a much more amplified, you can see that they disagree in the deep tropics and also disagree in the high latitudes. And so if you take a look at the feedback patterns in these 2 models, you can actually see they're quite similar and different in certain respects. So if you look at the subtropics going towards the high latitudes, you see this negative feedback that tends towards a more positive feedback in the higher latitudes. That's also seen in the Muroc ESM model, but largely where these two are disagreeing is in the deep tropics. So in CSSM4, it's a quite negative feedback pattern that's narrowly peaked and then goes more negative, whereas the Muroc ESM model, it's much more positive and more narrowly peaked than this model. And so if we just kind of do a thought experiment with this energy balance model, we can say that let's prescribe a spatially uniform ocean heat uptake value and radiative forcing. So any spatial variability is going to come about from whatever we prescribe as lambda. And so if we run this model, the energy balance model, with lambda equal to the global mean value of the feedbacks from CMIT5, just spatially uniform, we can also run it with a pattern that has a more narrowly peaked pattern like we saw in the Miric ESM model. And what you see is that when you run this, you actually get very similar patterns of warming. So you get equal degrees of polar amplification in both hemispheres, and despite having a completely different feedback pattern here, you get a very similar temperature pattern response with maybe a little bit more muted or amplified warming on the equator. But when you look at the P-E responses over here on the right, you see that they changed quite a lot. So in the uniform pattern of feedbacks, you get a kind of similar response between the Held and Soden scaling and the energy balance model in the deep tropics, but they diverge in the polar regions, which we can talk about later. But if you look at the tropics of the feedback pattern where the feedback is more narrowly peaked, you actually see that there's this kind of increase in P-E on the equator and a narrowing of the ITCZ region. And so what's really neat about the energy balance model is it's quite simple to understand. So you can take a look at the P-E conservation statement for the Hadley cell component of this model, or the energy balance model, and you can break this up into a thermodynamic term, which is just the fixed circulation times the change in moisture, or you can break it up into the dynamic terms, which account for the changes in the circulation. And so plotted here on the left is, again, the pattern of feedback where it was just spatially uniform, and the Held and Soden and moist energy balance model largely agree. And on the right here is now the pattern where they disagree, where the feedback is much more narrowly peaked. And if you write this out with each of these terms, you can see that this red term, which is fixed circulation, largely agrees with the Held and Soden approximation, which is what the assumption there was doing. But if you add in these purple terms, these change in circulations, you see there's little to no change in circulation when there's this uniform feedback pattern. But when you have that narrowly peaked feedback pattern in the deep tropics, you get a large change in circulation, which increases P-E in the energy balance model in the tropics. And so we can start to ask, well, what's causing these circulation changes? And we also can rewrite the change in circulation in the energy balance model to be a function of two different terms. So it's going to be a function of changes in the poleward energy transport by the Hadley cell, which is that Gaussian weighting function, or changes in gross moist stability in the energy balance model times this fixed circulation. And so I've just plotted these two terms here, where this is the divergence of atmospheric energy transport. This dotted line right here is going to be showing the uniform pattern, and then green is showing the feedback pattern narrowly peaked. And what you see is that there's just larger energy transport when there's that narrowly peaked pattern that must be transported poleward. And over here on the right is the gross moist stability changes, which are very similar across the two simulations. And it's just really a function of the warming in the model. But if you translate this into the circulation changes, you actually see that the energy transport, which must export it from the tropics towards the higher latitudes, it strengthens the Hadley cell a lot in the model, or the simulation in which the feedback pattern is narrowly peaked. And so gross moist stability tends to weaken the Hadley cell in both hemispheres, whereas the strengthening of the heat flux strengthens the Hadley cell. And so what you can see is actually that where this is peaked and where this is negative, the two combine such that there's an increase in the strength of the Hadley cell in the deep tropics, but a weakening of the Hadley cell in the subtropics, which is helping to change the spatial structure of the Hadley cell, and thus the moisture flux in the deep tropics, and increase P-E on the equator. There's kind of a more detailed explanation for this in Nick Seiler's paper, but I think that it's important to kind of show too, you can actually break down the P-E changes in the higher latitudes. So now you're looking at the extratropical regions of these two simulations, which disagreed from the moist energy balance, or the Held and Soden scaling, a lot too. And we actually can relate this to this second term here, which is just a change in the polar moisture flux. So largely the region you get a better agreement between GCMs and the energy balance model in the high latitudes is just a reduced moisture flux, which I can just gloss over here. But wanted to quickly highlight just some other work I'm doing with this, which is relating the energy balance model P-E changes to individual feedbacks as well. So that plotted here is just the surface albedo feedback, relative humidity, lapse rate, shortwave, and longwave cloud feedbacks. And so I'm going to gloss over this quite quickly, and I'm happy to talk about it later, but you can rewrite this energy balance model equation to basically say that a change in P-E to do one feedback is going to be a change due to the local feedback operating on that total temperature, some of the feedback interactions in the energy balance model, and then any changes in the heat transport of the model as well. And to maybe just more intuitively show you what I'm doing here is you take the energy balance model and you can remove the ice albedo feedback and examine how that modulates the wet gets wetter, dry gets drier paradigm. And so plotted here in black is the full energy balance model P-E changes. In orange is when I've removed the surface albedo feedback. So then green is the contribution of adding that feedback into the P minus E changes. Effectively, it's this term right here. And if you break this up, you can see how that pattern arises in the energy balance model and according to these three terms, where this is term 1, term 2, and term 3. And you can see that the changes in the energy transport is largely setting P minus E changes in the deep tropics. But as you get towards the higher latitudes, it's this pattern of feedback and the interaction between that temperature and the feedbacks itself that's helping to change P minus E. And so we can do this for other feedbacks as well. So here's the lapse rate feedback. So when you add in the lapse rate feedback, you actually decrease precipitation on the equator, increase precipitation in the subtropical regions. Again, we see that this is largely driven by this term 3, which is this sensible heat transport changes. And I think one of the more interesting one is back to kind of connection of what I showed earlier. If you remove the long wave cloud feedback, which is largely allowing there to be this more narrowly peaked pattern, you actually increase precipitation on the equator when you add that feedback in. So it's really saying that this cloud feedback is one of the drivers of this narrowing of the ITCZ and the increasing of the P minus E on the equator here. And you can see that that's really driven again by these circulation changes, which is altering the energy transport in the deep tropics. One last kind of plug for this is you can run this with all different GCMs that we have from CMET 5. So plotted on the top panel is just the spread of each of these feedbacks. And the middle panel is going to be the response of P minus E to adding those feedbacks in, where I've just shaded the sigma and 2 sigma spread from all of the 27 models. And on the bottom is the fractional contribution to this total variance. So you can think of it as the contribution to the uncertainty in P minus E. And so effectively you see that the shortwave and long wave cloud feedbacks are what's really driving uncertainty in P minus E changes across a range of latitudes. But if you look at the surface albedo feedback, you actually have a slight contribution from that on the equator, and particularly especially with the extratropical regions and the high latitudes. And so just as a quick summary of what I've shown here is that changes of the strength of the Hadley cells greatly impact P minus E changes in the tropics. These circulation changes are linked to the spatial structure of the radiative feedback. So a narrowly peaked radiative feedback pattern acts to strengthen the polar heat flux locally and then increase that moisture heat flux or that moisture flux on the equator. We also kind of talked about how polar moisture transport changes play a large role in setting P minus E changes. And then I was just kind of illustrating how radiative feedbacks alter the wet gets wetter, dry gets drier paradigm. So the surface albedo feedback can shift the ITCZ through atmospheric energy transport changes. The long wave cloud feedback acts to narrow ITCZ. And then the short wave cloud feedback is really the greatest source of uncertainty in P minus E changes. So with that, I'm happy to take questions. And first part of this has been written up and submitted, and the second I'm currently writing up. So thank you.
Awesome, Dave. Thank you so much. That was very interesting. So we have time for a couple of very quick questions, maybe one or two. I guess we already have one from Andy. Is this a one-dimensional or two-dimensional EBM? If 2D, have you looked at spatial patterns of the changes?
Yeah, so this is a one-dimensional moist energy balance model, but I do think it would be interesting to extend this to like a longitudinal direction, see how well it works. Yeah, it'd be a great idea.
And we have another question from Chenggang. How did you compute the local feedbacks?
Yeah, this is a good question given the pattern effect theme from this seminar series. So we computed as a local radiation divided by the local temperature. So it's still the local perspective that maybe has some bias in exactly how you run this. So I think we've talked to some people about extending this work to include a Green's function approach to the feedbacks in this too. So yeah.
And one last question for now from Nick. In the scatter plot comparing the MEBM and the HS06 scaling, I guess that held in Soden, in different regions, what was the metric on the y-axis?
Yeah, that was, sorry, I kind of glossed over that. Let me just, so it's actually just showing the GCM's averaged P minus E response on the y-axis, and then the energy balance model or held in Soden on the x-axis. And this is just the one-to-one line. And so each of these are just different regions. All of them are different models. Red is the held in Soden, blue is the energy balance model. And then I've just calculated the correlation coefficient here. So it's just showing how well, what's the skill of the energy balance model relative to held in its own scaling.
Cool. Big differences in the high latitudes. Okay, so we're gonna move on in the interest of time, but you're welcome to continue the conversation in the chat.
All right, so our second speaker today is Dr. Gavin Schmidt from NASA GISS. And I think he's gonna talk about the possible implications for climate sensitivity from anomalous freshwater additions from Antarctica and Greenland.
Okay, thank you very much. Yes, I mean, the title says it all. And this is, let me just explain what I'm talking about here. There are real model and observation discrepancies in the Southern Ocean. I think we may all be aware of that, but I'll just go through them. The temperature changes, the salinity changes are very large differences between the CMIP 5-6 models and the observed trends. The trends in Antarctic sea ice are at odds with what's been observed. There appears to be quite a large discrepancy between top-down and modeled carbon uptake in the Southern Ocean using similar models. We know that the Southern Ocean is a key area for the enhanced positive cloud feedback seen in the high ECS CMIP 6 models. The work of Mark Zelinka and all makes that abundantly clear that this is an absolutely key area for the ECS, particularly the high ECS models. And we know that there are missing processes in the CMIP 5 runs and the CMIP 6 runs. Notably, none of the models have net freshwater loss or anomalous freshwater loss from ice sheets and ice shelves. They don't include mountain glacier loss or reservoir construction that affect the terrestrial water budget. And recent analyses, and this is what I'm going to show you today, recent experiments and analysis suggest that including these processes can greatly reduce these discrepancies, and then that is going to have some consequences. So let me just briefly kind of illustrate what I'm talking about here. This is from a very recent paper by Chung et al. And you can see on the bottom the CMIP 6 ensemble. In the Southern Ocean, you get muted warming, but you don't get cooling. But in the real world, we've seen cooling. In the sea ice, we've seen decreases in sea ice. And in the models, we get just decreases in sea ice. And so there's a very clear distinction between what's happening in the models and what's happening in the real world. In the carbon uptake, this is from the global carbon budget from last year. There is an increasing divergence between the ocean sink estimates of carbon as determined from observations and from what's being determined from the global models. And that's increasing as a function of time and becoming quite discrepant. We know that there is anomalous fresh water coming from the ice sheets. So we can measure, this is from gravity measurements from GRACE and GRACE follow-on, that Antarctica is losing about 150 billion metric tons of ice a year. Greenland is losing about 280 gigatons of ice. And that water is, of course, going into the ocean. But it's not just the grounded ice that's going away. We're seeing actually much larger shifts in the ice shelves. And so if you look at the highlighted levels in those tables, and you look at the 94 to 2017 column, which is the last column, what you see is that the fresh water from ice shelves, which are floating ice, actually dwarfs the amount of water that's coming off the continent itself, almost a factor of 2 or 3 larger. And so that means that we're talking very large amounts of fresh water indeed. Now, a lot of times people neglect the change that's related to floating ice because the impact that floating ice loss has on sea level is small. It's not zero, but it's smaller by a factor of about 37 than if that ice was melting had it been on the ground. But the impact of floating ice loss on salinity is exactly the same as if it was grounded ice. And so if you're looking for ocean circulation or steric effects from changing ice, you have to include the loss of floating ice as well. Okay, so I'm going to look at some GISS model runs here. This is our kind of standard introduction. We do a pretty good job over the historical period. The climate sensitivity is pretty much ballpark. TCR is in the middle of the pack, and notably, this model, which is the red line in the sea ice area graph there, it does a very good job. At least compared to previous GISS models, doing Antarctic sea ice and ocean properties in that region. And so this is a good basis for us to be starting. Meltwater from the ice sheets is distributed regionally around both Greenland and Antarctica. We have two variations of that. So loss of grounded ice, both in the climatology or in the anomalous changes, is distributed over the top 400 meters of the water column right next to the continent. And then there's like a larger area of addition from the loss of floating ice, which is assumed to kind of follow the patterns of iceberg distribution and the like. These are pretty ad hoc patterns, and so there's some uncertainty associated with that, of course, and other models would do something different. So. And what we've done is we've imposed anomalous freshwater, both in terms of idealized scenarios, such as the ones on the left here. So an idealized scenario of 500 gigatons of fresh water, or 2,000 gigatons, or 5,000 gigatons, which is obviously a lot. And we've also done changes that are kind of based on historical estimates of these changes, which you see on the right. And there you can see that the amount of fresh water that's coming off Antarctica has reached about 800 gigatons per year, a little bit less in Greenland, but these are quite large. These are quite large amounts. When you do that, and we've done this in a number of different ways, what you find is that the impacts of Greenland and Antarctica are basically additive. They don't really intersect very much, and they're basically linear in the forcing. There's some saturation that happens, but the more fresh water you put in, the more of a change that you see. Now, when you do the historical additional fresh water, and so here on the left is the historical trends in our the surface air trends. Surface air temperature trends in our historical runs that are the standard 6 runs, and then this is the other graph is the difference when you add the additional fresh water. What you find is that the only places where there's really statistical significance is right around Antarctica, maybe a little bit in the North Atlantic, but mostly around Antarctica. And if you look at that in the zonal mean, it becomes a little bit clearer. The blue line at the back is the zonal mean trends you see in this model over 1990 to 2018 without any additional fresh water, and then the red line is what happens when you add that fresh water. And what you see is there's a very clear difference right next to the Southern Ocean, right next to Antarctica in the Southern Ocean, and where you actually see in the zonal mean we're seeing cooling for the first time, which matches the GISS temp analysis of temperature, which in this case, because we're looking at SST, comes from the ERSST version 5 product from NOAA. Now, different analyses of the ocean temperatures give you slightly different amounts of Southern Ocean cooling in slightly different places. There's a difference in the ERA 5 analyses. There's a difference in the AIRS analyses, but this the GISS numbers seem to be kind of in the middle of those different estimates. You see some minor differences in the North Atlantic, not really statistically significant, but you can see it also going a little bit closer to what we've inferred from the observations. The impacts on sea ice are also noticeable. So in our historical runs, we also saw a decrease in Antarctic sea ice. If you add the freshwater addition, then that reduces, and so you end up with trends that are now consistent, at least within the noise of the observations, which wasn't true before. But what's causing the Antarctic melt, right? That turns out to be very important. And here I'm gonna dig back into kind of GCM prehistory and show a result from CMIP3, which I find remarkable. But anyway, this is a graph that appeared in Miller et al. 2006, where we were looking at the impacts on the annular modes of various configurations of the GCMs, and CMIP3 was interesting because half the models had ozone and ozone hole forcing, and half the models did not. And the runs in red here, they had an ozone depletion and they had an ozone hole and then a recovery post 2000, whereas the blue ones only had greenhouse gas forcing effectively, with no real changes to ozone depleting substances. And the interesting thing was that there's a very clear separation between those two sets of models in what happens to the southern annular mode. And you can see that the models that had the ozone forcing predicted a much stronger change to the southern annular mode than the models with just greenhouse gases, but that all of them showed an increasing positive trend in the southern annular mode, so increasing westerlies around Antarctica. And so you have over this period, both the ozone depletion and greenhouse gases, particularly CO2, are working in concert, pushing the southern annular mode towards a more positive phase. And since this was published, I've added in the observed changes in the green line, and you can see that the models with the ozone forcing actually had a skillful prediction of what would happen to the southern annular mode. And so I think we should go back to our previous predictions more often than we actually do, and in this case we did quite well, collectively. And so why am I talking about that? Well, the idea is, and there's some question marks on this, but the idea is that both ozone depletion and CO2 increases push the SAM into a positive state. That causes warm water to upwell onto the Antarctic shelf, which melts the ice sheets and ice shelves from below, which then is leading to freshening, stabilization, and cooling. And then the idea then would be, well, that's going to reduce Southern Ocean cloud feedbacks and therefore produce a smaller ECS if we include all of these things. Now, whether this is going to affect ECS or not really depends on whether the ozone depletion or the CO2 are the dominant term, because if it's CO2, if this is a process that is driven mainly by CO2 for seasonal reasons or for some other reason, then you might expect it to have a large impact on ECS. if the impact is really just being driven by ozone depletion, which is not part of a 4 times CO2 or a 1% times CO2 issue, then it won't be. And so we have to think about climate sensitivity a little bit more broadly than just the effective climate sensitivity that we're calculating right now. It depends both on time scale and on included processes, and the changes that we're seeing here, these are not the slow changes in ice sheets that people have tried to kind of rule out from climate sensitivity. These are fast changes to ice sheets and oceans that really kind of comes like smack into the definition of climate sensitivity as we currently envision it. So it's not a negligible thing, but I don't know how big an impact it's going to have. So let me just summarize. Including observed anomalous freshwater and historical runs greatly reduces the discrepancies with observations in the Southern Ocean. It produces cooling, it improves the sea ice trends, and I think we haven't finished these runs, but I think it's going to improve the carbon uptake estimates. This both reduces the residual SST that you kind of have to explain from looking at pattern effects and the like, which will impact ECS constraints from the historical period. Drivers of anomalous freshwater are likely a combination of ozone depletion and CO2 via the enhanced southern annular mode, and therefore it implies that inclusion of dynamic ice sheet and ice shelf loss in like kind of standard 1% CO2, 4 times CO2 runs would show analogous effects, reducing Southern Ocean cloud feedbacks and hence both TCR and ECS responses. This is not a slow feedback that is only important for, say, the Earth system sensitivity. This is a feedback that is relevant today and in the transient period that we're most concerned with. And because of the carbon uptake effect, it may actually even have an impact on the transient carbon response as well. So thank you very much.
Thank you, Gavin. That was a great talk. So if you have questions, remember to either raise your hand using the raise hand reaction or type the questions in the chat.
All right, I just need to go and plug in my computer. Okay.
Okay. Cece has her hand up. Cece, go ahead and unmute yourself.
Hi, that was fun to hear about your recent work there, Gavin. I'm curious, though, you talked about the scenarios of freshwater as being kind of suddenly on. Was that the case for your historical runs, or were those transient? And if they were transient freshwater, how high does it reach in gigatons?
Yep, that was on this slide here. So the historical ones were using, historically constrained estimates of the freshwater loss that you can see in the on the right there.
On the far right.
So the Antarctic losses, including the floating ice shelves, reach about 700 gigatons per year in recent years.
And it's more for Antarctica, because I was kind of confused. I thought you said
because there's been more thinning and loss of floating ice shelves.
the shell.
So the
right.
Yeah,
Okay.
so the loss from grounded ice is smaller, but the loss from floating ice is larger.
Okay, thank you.
Andrew asks, how big a change in ECS will result from this? Yes, I don't know. To be able to answer that, you have to have a credible dynamic ice sheets and with ice shelf ocean interactions done in a reasonable way, and we do not have such a model, and I don't know really that anybody else does either. But it's not one can make an estimate, kind of making, if you assume that all of the freshwater forcing is due to CO2 now, you might be able to say something, but I haven't done that calculation. Zhu Zhang, is there any and how much change in the strength of the AMOC? Yeah, so the changes in the AMOC are not that large. We're talking a few Sverdrup, and so they're barely detectable and not really that different from the changes in AMOC in the runs with no additional freshwater forcing. I attribute warming to the SAM plus the trend, yet the net effect is cooling. Has any I'm not quite sure, Dennis. Do you want to expand on that? What warming have I attributed?
Yes, you said that the SAM, the winds moving, strengthening, would cause upwelling of warm water, which would warm things up, and that would melt ice, and then the fresh water would result in, so the net effect is net cooling. So you have net cooling, yet also enhanced.
Yeah, well, so that's, it's happening at different levels. So the upwelling of warm water is at depth, and the cooling is at the surface. So what we're seeing is an increased what we're seeing, if you look at the zonal mean picture, you're seeing cooling right at the surface and then warmth underneath that.
So the shelf ice is melting from below, and yet the surface is cool. Is that what you're saying?
Yes.
Okay. Thanks.
Yudang, the impact of freshwater on radiative feedback is mostly confined to the Southern Ocean and can reach the tropics through subtropical cloud feedback change. So that's an interesting question. And so when we've done these runs with just a big input of meltwater, we do see changes that propagate from the Southern Ocean to the rest of the planet, mostly through changes in water vapor and the like. And so yes, it can. I don't know how important that would be in the historical cases, because there the changes in the freshwater additions are much smaller than in the big experiments that we did, where we were looking for just such a result. So yeah, so there's a possibility of this increasing and becoming more global, but I don't know how large an effect that would be practically.
Okay, thank you. In the interest of time, we should move on to our last talk. But thanks again, Gavin.
Yeah, great. So our last speaker today is Geeta Persad from University of Texas. And I believe she is going to tell us a story about the role of anthropogenic aerosols in the pattern effect.
Great, thank you for that introduction, and thank you for framing it as telling a story, because I'm going to be sort of presenting a discussion today of the potential role of anthropogenic aerosols in the pattern effect, and particularly in the time evolution of the global feedbacks over the historical period. And I'm expecting that this talk will produce more questions than answers, hence the extra question marks on this title slide. So I look forward to this discussion, but I'll start off by introducing how I'm thinking about this problem of pattern effect. I'll share some results that start to hint at how aerosols might play into these issues. And then I'll close with some open questions that this raises for me. But I hope by the end of this to convince you that it's worth for us to think more critically about the ways in which the time evolution of aerosol spatial pattern might influence the time evolution of climate feedbacks, and therefore the estimates of climate sensitivity that we're making based on the historical period. Okay, so what use of the phrase pattern effect am I using here? So I'll just be using the phrase pattern effect to refer to basically any variations in the strength of global mean feedbacks that we think are dependent on the spatial pattern of forcing or response. So for example, here I'm showing the time evolution of global mean effective radiative feedback parameter, lambda from Yue Dong's 2021 paper. So the more negative lambda is more strongly damping feedbacks and consequently lower overall climate sensitivity. And the black line here is showing how the strength of feedbacks evolve in historical, all forcing, fully coupled climate model simulations. The pink line is showing what that looks like for historical greenhouse gas only. The dark red bar shows what that looks like for quadrupled CO2 simulations. And you can kind of eyeball and see that the feedback parameter in response to a quadrupling of CO2 is slightly less negative, less damping than the historical all forcing simulations would suggest. And then finally, this blue line is the feedback strength in simulations where that are run with observed sea surface temperature, which give a much more negative feedback parameter and imply lower climate sensitivity than fully coupled historical simulations. So understanding what drives the evolution of this feedback parameter, and particularly the difference between the values that you get from the historically fully coupled simulations and versus observations versus quadrupled CO2 experiments, right? This is really critical for understanding what the effective climate sensitivity of the climate system is and what we should expect. So I know many people here are thinking about this a lot, but just to frame kind of where I'm thinking about this from. And of course, UA's work and others' work has also given us these Green's function approaches and other theoretical approaches that theorize that this time evolution in the feedback parameter is connected to the higher ability of patterns with warming in the Western Pacific to drive strong negative cloud and lapse rate feedback. So depending on how our pattern of warming is aligning with these patterns of high sensitivity or strong feedback responses, we'll get different strengths of the overall feedbacks. But there's pretty limited understanding of the role that anthropogenic aerosol emissions over the historical period play in this picture. So in the same 2021 paper, UA used DA-MIP simulations to look at how the effective climate sensitivity derived from historical aerosol-only simulations, which are shown here in yellow, compare with the ECS that you get from fully coupled simulations, which are the black bars here, or the quadrupled CO2 experiments, which are shown here in pink. And the first thing you see is that there's really high variability in response strength across the DA-MIP models. So in particular, anthropogenic aerosol forcing produces lower ECS, i.e. more damping feedback than total historical forcing in about half of the models. And then in the other half, it produces a larger effect. In the multi-model, we think that there's slightly higher efficacy of historical aerosols compared to historical all historical forcings, but the uncertainty is large, right? And then even more recently, Pietro Salvi et al. Did a more detailed CMIP6 multi-model comparison of the feedback strength here from historically fully coupled simulations in green. And then in blue is from the aerosol-only simulations. And now this is showing it relative to the strength of the greenhouse gas feedback. So downward here is feedback's more amplifying than greenhouse gas only. And again, you see this big spread across the different models, which are all these different bars here are different models in the CMIP set. And then on the right hand of the dashed line is the multi-model mean. And so they find that feedbacks in response to historical aerosol forcing are overall more strongly amplifying than in response to historical greenhouse gas forcing. And so consequently, the historical total feedbacks where you have a negative aerosol forcing combined with positive aerosol greenhouse gas forcing is more damping than it would be with only greenhouse gases, and that lowers the overall climate sensitivity. And they attribute this to the fact that aerosols are primarily located in the northern extratropics, where you have a shallower temperature response that creates these stronger amplifying cloud and lapse rate feedbacks. And these findings align well with work that's been done by Drew Shindell, Jim Hansen, and others going back to the early 2000s that suggests that aerosol forcing has a higher climate efficacy than greenhouse gases due to its particular spatial distribution. But notably with both of these assessments is that we're looking here at the historical average, right? And arguments that are made about the drivers of this efficacy are based on the historically averaged aerosol spatial distribution. The complicating factor, though, is that we know that the spatial pattern of aerosol forcing has evolved substantially over the industrial period. So those historical means are actually the time integral of a series of different aerosol-driven pattern effects that may be canceling or amplifying each other through time and may be driven by different processes, right? So just to illustrate that, I'm showing here trends in aerosol optical depth for 30-year periods from the 1930s through present day, and the maps on the right-hand side here, these are from the CESM1 large ensemble, Desser et al. 2020. And then on the left-hand side here is the continuous evolution of AOD in North America and Europe on the top, Southeast Asia in the middle, and South America and Africa in the bottom. And you can see this migration in aerosol optical depth over the 20th century from sort of northern hemisphere mid-latitudes into sort of the tropics, and then into South and East Asia. So you have this sort of redistribution. And this creates this evolving spatial pattern then of the climate response to aerosols. So this is what I'm showing you here in the sea surface temperature responses. So the right-hand panels here are the same 3 time periods showing now the spatial pattern of SST response in response to aerosols only. And then the left-hand side is what the all forcing simulations do over those same periods. And so you can see that the aerosol-driven SST trends have fairly different patterns across these 3 periods. And when we look at the all forcing historical trends, certainly the overall warming is greenhouse gas driven. So the global mean is driven by the greenhouse gases. But the pattern of deviation from the global mean bears a really strong relationship with the pattern of the aerosol-driven SST change. And I just want to note that particularly because we have reason to think that it's the pattern of deviations from the global mean that drives the pattern effect as opposed to the absolute spatial pattern. And I'll come back to that later. So the big question that this raises for me is, what does this mean for the time evolution of radiative feedbacks via the pattern effect? So when we combine this time evolving spatial pattern of aerosol-driven SST change with these Green's function types approaches that UA and others have given us that tell us how spatial patterns of warming are connected with global mean feedbacks, how much of that historical time evolution of the feedback parameter can we explain? All right, so if we look back at that historical evolution that I showed before, what would adding a historical aerosol only line to this look like? So how much of the variability in the historical coupled line does that explain, especially in comparison with historical greenhouse gases? And then I think it's just sort of an interesting thought experiment to think about, we have this big difference in recent years between the feedback parameter that we get from fully coupled simulations in black versus observations in blue. And I think it's just interesting to think, we know aerosol forcing is very uncertain, aerosol responses are very uncertain. How wrong would we have to be about the aerosols to explain this? I think it's definitely not all of the explanation, but it would just be interesting to think about how wrong we would have to be. So I'm going to present results from a paper we did a couple years ago that shows how the efficacy of aerosols depends on where they're emitted from. And then I'll show some preliminary analysis that tries to scale up that thinking into how this would manifest in the total aerosol contribution to this time evolution as the global spatial pattern evolves through time. Okay, so a few years ago, I did a study that was not motivated by the pattern effect at all, but I was wanting to understand how the climate response to aerosols depends on who's emitting them. So we wanted to test the climate influence of basically taking the same chunk of aerosols. Here we used an amount of sulfate black carbon and organic carbon that was roughly equivalent to what China emitted in year 2000. So you take the same chunk of aerosol and you just emit it from different regions. So here we just put it in each of the 8 regions that you see on the map here, kind of tracking major past, present, and future projected emissions hotspots of aerosols. And this was done in CESM1 with the Slav Ocean. And these were equilibrium simulations. And we found in the process that there are major differences in the global mean temperature response that don't necessarily scale with the differences in radiative forcing. So big differences in the efficacy. So that's what I'm showing you here. On the y-axis is the global mean surface air temperature response to putting identical emissions of aerosols in each of the 8 regions. And on the x-axis here is the effect of radiative forcing. And so you can see you get a big sort of order of magnitude difference in the temperature response and a smaller range in the radiative forcing response. But you get about a 5-fold difference in the efficacy of that forcing. So places like India have very low forcing efficacy, whereas places like Western Europe have very high forcing efficacy. And it just so happens that the places that have relatively high efficacy, Western Europe, the US, China, were the sort of past emitting hotspots. Whereas the places that are projected to be major emitting hotspots, so India, Indonesia, Brazil, South Africa, East Africa, they happen to have fairly low efficacy. So we can summarize that efficacy value in this chart. And again, you can see that kind of distinction between sort of the past emitters, Western Europe in yellow, the US in purple, China in green that have high efficacy, places like India and South America and Africa that have pretty low efficacy. So this obviously gets you thinking about what this means as the spatial pattern of aerosols evolves across these different regions, which I'll talk about in a minute. But we wanted to understand what was driving these efficacy differences. So we used radiative kernels to quantify the strength of individual feedback changes in response to forcing from each of the regions. So I'm characterizing that here with a term that I call radiative gain. It's really just the feedback strength divided by the regional forcing. So it's just telling you how strongly a given regional emissions forcing generates a given feedback. And so what you can see here, I'm just showing you the variations in global mean total cloud and ice albedo feedback in response to forcing from each region. And I'm just showing you those two because the variations in these two feedbacks drive roughly 90% of the overall variation in the efficacy. So based on this, we would propose that it's the differing ability of the spatial pattern of forcing in each of these regions to generate these cloud and ice albedo feedback processes that then drive this distinction that we get in the forcing efficacy. Right, so then we have this fact that the past emitters happen to be high efficacy and the future emitters happen to be low efficacy. So how does this scale up to the evolving global spatial pattern that we've actually seen historically? Because this suggests that perhaps past aerosol patterns might produce a higher efficacy than the present or projected future patterns. So just to kind of illustrate that, here I'm showing you the spatial distribution of sulfate emissions in each time period from 1950 on the left, 2000 in the middle, and 2050 on the right. And this is just kind of giving you a sense of the overall spatial distribution of anthropogenic aerosol emissions. And again, you can see the sort of redistribution from really strong sort of Western hemisphere emissions in 1950 to more strongly sort of Chinese and tropical dominated emissions. And then in the future projections, we're looking at potentially concentration into parts of South Asia. And so to explicitly understand how this evolution of the spatial pattern could affect the climate response and the efficacy, we based a set of preliminary experiments that test the climate response to just changing the spatial pattern of emissions, independent of changes in the amount. So we basically took the year 2000 amount of emissions and then distributed it according to the 1950 pattern and then according to the 2050 pattern. And then we ran equilibrium experiments for each of these three situations and looked at how the climate response differs. Right, so the goal is assessing whether we get significant differences in the climate response to aerosols just from changing the spatial pattern. And we find that in general, the change in global emission pattern alone does produce changes in efficacy, but it's not necessarily what you would expect from those region by region simulations that I showed before. So here again, I'm just showing you those three spatial patterns of the actual emissions. And then on the bottom here are the three spatial patterns of temperature. And they're largely similar, but there are some notable differences in the spatial pattern. For example, the pattern over Asia, and you can kind of get a hint that the overall strength is a little bit different. So again, we have the same amount of emissions in each of these cases, and they're producing different strengths of response just based on this difference in pattern. And we can see that more explicitly here. So here I'm showing you on the x-axis, the global mean effective radiative forcing, and on the y-axis, the surface air temperature change in response to the year 2000 pattern in green, the 1950 pattern in blue, and the projected 2050 pattern in red. So the year 2000 pattern produces both the strongest temperature response and the strongest forcing, but the efficacy is also higher, which are the numbers that I've summarized here for you. The efficacy is higher for the year 2000 pattern than for the 1950 or 2050 pattern, which are statistically indistinguishable. And that's perhaps not what we would have expected based on the region by region experiments, right? We expected that the past emitters would have a higher efficacy than potentially the present day distribution. And this points to potentially nonlinearities when you have multiple regions emitting and forcing in tandem, and really highlights the importance of sort of explicitly testing how these sort of more idealized frameworks scale up to the global. But it does indicate that these realistic historical variations in the spatial pattern of aerosols can change the overall efficacy of the aerosol forcing in a way that's statistically significant, at least within this one modeling framework. Again, this is very preliminary. But so just to summarize the highlights from what I've shown, we found in that first study that the aerosol efficacy can span this 5-fold range depending just on the source location. So taking the same amount of aerosol and just moving it around. And it just so happens that emissions from past source regions have a higher forcing efficacy than those from the major present and projected source regions. And so this might lead us to think that you would have a certain evolution in the overall efficacy of the evolving global pattern. And when we actually explicitly test that, we see that the turn of century, sort of year 2000 global aerosol pattern actually has a stronger efficacy than the 1950, mid 20th century, or the projected mid 21st century pattern. And so potentially here we have some nonlinear responses that may muddy this, but I think it raises an interesting question too of how heterogeneous is heterogeneous enough to produce these differences in efficacy. So both, different patterns from each other, but also relative to more homogeneous greenhouse gas forcings. So where does this leave us in terms of a role for anthropogenic aerosols in the pattern effect? So coming back to that figure from UA's paper that I showed before, here I've added on top just a very naive estimate of the effective radiative feedback, assuming that those simulations that I showed are equilibrated and that the feedback parameter is just the inverse of the forcing efficacy. So here I've added on what we would get from the 1950 aerosol pattern, from the year 2000 pattern. 1950 is about lambda of about 1.1, 2000 is about 0.9. And then the individual regions from the earlier paper span roughly a 1 watt per meter squared per Kelvin range. And these are obviously very rough estimates, but they suggest that this evolving spatial pattern, sort of realistic historical evolutions in the aerosol pattern, could produce differences in the feedback parameter that are similar in magnitude to the time variations that we see in these historical coupled simulations. We certainly need to do this continuously and account for model uncertainty, which we know is extremely high for aerosols. So the DA MIP runs can certainly help with that, but even with that, we have signal to noise issues for anthropogenic aerosols. So multi-model single forcing large ensembles that are coming online will help us get a better picture of this. And I'm actually co-author on a paper that was just submitted that proposes a protocol for single forcing large ensemble MIPS led by Doug Smith that might get us a little bit farther toward this. But I think this time resolved analysis is particularly important, not just in terms of understanding what happened historically, but also because we expect that aerosol patterns are going to evolve substantially over the next several decades, right? So coming back to the importance of deviations from the global mean pattern, not just the absolute pattern, even if aerosol's global mean effect is waning relative to greenhouse gases, their impact on the time evolving spatial pattern of deviations from the global mean may still be substantial for the foreseeable future, right? So understanding how important the spatial pattern is will be valuable for anticipating how projected future anthropogenic aerosol changes might manifest in our estimates of feedbacks and ECS based on simulations or observations, and also how they've already been doing that, right? So are they going to maintain or counteract the historical pattern effects that have affected our thinking of what ECS is? And then I think doing this temporally resolved analysis also just gives us a different dimension over which to try to unpack all of the uncertainty that exists in the historical aerosol efficacy across climate models. So do they all produce similar time variations, but just with a different total magnitude? Does all the bias come from a particular time period where a particular spatial pattern dominates? Can that help us pinpoint forcing or feedback processes that are driving that model spread? So I think these are all interesting questions that we could get from basically adding a historical aerosol line to this in a way that appropriately accounts for model variability. Okay, so I hope this has given us some food for thought on how we can gain a deeper understanding of what has been happening historically with radiative feedbacks and ECS, and also what may happen in the near future by unpacking this effect of the evolving spatial pattern of aerosol emissions, which I think we haven't really been thinking about that deeply when we try to consider the overall variation or even the role of aerosols in the historical feedbacks in ECS. So with that, I look forward to discussion, and please feel free to reach out to me via email if we don't get a chance to discuss today. Thanks.
Thank you, Geeta. Definitely a lot of food for thought. So we're at time. So people that want to hang around for some more Q&A and some discussion are welcome. But for everybody else, we just wanted to thank you for joining us, especially during the summer. And we'll let you know when the next one will be. It will not be in July because CF MIP is happening about a month from now, and there's a lot of overlap. So with that, let's thank the speakers, and please hang around for some Q&A with Geeta.
So I see Norm has a question in the chat. he's asking if regional differences in aerosol type are accounted for in those simulations, and the answer is no. We deliberately kept the aerosol mix the same across different regions. So it's the same mix of sulfate, black carbon, and organic carbon in each region. I would say overall, the response is largely sulfate driven. So I don't know how much the mix would impact things, but I think it's, it's worth understanding more.
So I have a question for the single forcing ensembles that are being proposed. Is there also going to be a paired RF-MIP type simulation to diagnose the effective radiative forcing? Because this confusion, this difficulty in disentangling what is the effectiveness of the forcing with constant SST and the efficacy of the feedback engendered through different SST patterns, I think it has posed some problems because there's almost never all the simulations you need to disentangle everything.
So unfortunately, no, I don't think there are RF-MIP style simulations planned as part of that, but one could conceivably use the smaller ensembles of RF-MIP type simulations and combine them with the large ensembles of response, just so that you kind of have both sides of the coin. And I think that could be feasible if we expect that the spread in the forcing is going to be smaller than the spread in the response. So having a larger ensemble is going to be relatively more important for constraining the response than the forcing. So that might continue to be sort of a tractable way of still getting benefit from these single forcing large ensembles, even if they don't have an RF-MIP type sort of companion run.
Or at least if they're run with the same model version as the CMIP6 RF-MIP simulations. Okay, thanks. There's one more question in the chat. I don't know if you want to read it out.
Yeah, so the question is, in the runs, does the role of wind and aerosol transport considered? And yes, these runs are fully interactive. So all that we're prescribing in the simulations is equal emissions. And then you have sort of distinctions that emerge at every step from there on. So we get differences in the actual concentration of aerosol that is sustained in the atmosphere, depending on the region and the spatial pattern. You obviously get difference in the spatial pattern of the emission, of the sort of distribution of the aerosols in the atmosphere. And then you get distinctions in the radiative forcing, and you get distinctions in efficacy that gives you even wider ranges in the temperature. So because we're prescribing emissions, we see these deviations across basically all steps of the life cycle of the climate response to the aerosols.
Interesting. Okay, well, if there's no more questions, this is probably a good time to end. Thanks again to Dave, Gavin, and Geeta, and we'll see you next time.
Thanks, everybody.
Yeah, thanks for the opportunity.
Yep, thanks. Bye.